I will try to finish this one today. Only 15 minutes. And if you have time to read our textbook, basically textbook will provide you more details about the modeling. And I won't go to the very much detail about the physical systems modeling because from every single class, every single class, like the fluid mechanics, like heat and mass transfer, like from vibrations, and even from your ES 307, and you should learn some kind of fundamental formulation for circuit. So here, this lecture here, I simply summarize the quick result for you, and you will see. The first one is the mechanical system, very typical mechanical system, and here we don't have mass, and we only have a combination of the springs. I believe you should have explored this one in vibrations already. Right now, today is lecture 4 or 5. So basically here, if you have two springs in kind of the parallel combinations, so the equivalent spring constant is this. So here we have K1, we have K2. And so if we want to equivalent to this, so simply we want to use one spring to describe. So here we can try is this, and in formula this one is K1 plus K2. Okay, and this one can be derived like this. For example, here we have a force applied to here. Then from Hooke's we know the force equal to this equation, the equal to force. Okay, so put together, you can see that is our equivalent spring constant. So in a similar way, if we have a series, the spring in series combinations, then equivalent spring constant should be K1, K2. So if we want to use the equivalent spring constant to describe, so this is a KEQ for this. So KEQ can be calculated using this formula, okay? And those are the detailed calculation you can refer to. Otherwise, I think in vibrations you should have a little more detail you can refer to there. And using this one, that will help us to simplify certain mechanical models. And the other one, this is the damping component. The damping components basically here in a similar fashion, if in combination, in parallel combination, the equivalent damping component is in this, and that is basically take the similar, the format like spring. So with those things, then we will be able to begin to formulate the traditional mechanical systems. Most of the mechanical systems are composed of the spring and dampers. And again, I like to use, and I've seen in some automobiles companies, and either in magazines or in the TV shows, they have their models for describing the dynamics of the car. Those models here basically, I think I've shown here a few times before. So if this is the tire here, if this is a car, they will be able to, for example, here in terms of the car, the wheel here, they will be able to simulate the dynamics of the wheel. For example, if this is a wheel, and this is the suspension, the shaft. So this will be some dampers, some springs, and then they might combine with certain very complicated know-hows of the different components in a certain way. Okay, so here I kind of exaggerate. So in different, the tier-wide, the combination of the spring constant and the damping component, and they do this one. Every car have their recipes for making these, and they will guarantee from there they pay the engineers to do this one on one side, they have the experiments to say sense to measure the dynamics of any point. That would guarantee, using this simplified model, the result of at a certain monitor point will be similar, very similar to what it should be. So that means the complicated, the continuous material model in terms of the car can be simplified as a discretized spring and damper mass combination system. So that is the whole idea of these things. And again, every single car has their know-how recipe for this, and that should be going to the secret of those things. And so with those kind of the motivation in mind, so the most simple, the simplest mechanical systems are described by this. And I think you have seen this one already a few times. So this is a mass, and this is a damping called the dampers is a spring. And here we have only one mass, and this mass can be a lump mass for, say, a human being. The weight of the center is just right at the tummy here. So if you like to simulate your whole body, you can simulate your whole body as a whole lump mass. So that's a one single degree of freedom system, right? So this is we have one mass. This one is called the one DOF, one degree of freedom system, and second degree of freedom systems can be like this. For example. So here we have two mass blocks. So here we have 2 degree freedoms because here we always assign. So once this mass has a weight, right? So this will be pulled by the gravity. So the spring will be deformed. This damper will be stretched out a little bit. But when the whole system is in static equilibrium, from that equilibrium positions, we define our degree of freedom. And say this called it, let me call this is called the, let me call Y1. Okay, call Y1. So this is in terms of the function of time. This is defined as the degree of freedom. And again, in all the mechanical systems, we define the degree of freedom systems, degree of freedom from their equilibrium positions. It's not from their undeformed position. I think this is the point you have to make very clear from your vibration concept. And in a similar way, here is the degree of freedom. We measure from the equilibrium of this mass block, then we call the Y1T, and this is called the Y2T. Okay. So now the matter is how can we describe the Y1T in terms of the system's features? And first question, so this is about the modeling. The second question, once we have modeling, how do we know the YT? How can we solve the equation for YT? Then furthermore, if we say this output, the dynamics is that we want this one to be tracking certain command. If it is not, how can we modulate the number K and C or even M to have this output to follow what we desire, and that is a control. So here is the 3 categories. The first category is how to do the modeling, how to describe this system, and here I'm going to show you one more time, but I think you have done this one in your vibrations. So again, and assuming this one under these equilibrium positions, and we assume, say, this mass block being moved down by a certain amount, okay? So here, from this positions, the mass has been moving down by here. Okay. So moving down by this one, so that is denoted by degree of freedom Y of T. And then you can see that right now spring for this, in terms of this configuration, has been stretched a little bit longer. So that means spring will try to apply the recovery force, and that is trying to pull it back. Okay, so that's a KY. Okay. And again, assuming everything is in dynamic situations, so at this moment, they have velocity, y1 dot. Again, here y is a function of time, so suppose we can do the time derivative. the velocity multiplied with the damping coefficients, and that is the force trying to repel this kind of movement. Okay, so that is the force. So this is about the force applications. And furthermore, if we would have external loading, so say here we have any kind of external loading, or what we call the external excitations. So that means additionally, we also have external loading applied to here. So here, once we have the distribution of the force on the degree of freedoms, then we simply apply Hooke's law, not Hooke's law, Newton's second law. Yeah. The force, all the forces components will be equal to m times velocity, not acceleration. Yeah. Okay. So that means here we can see all the forces, and here we take the sign, and here should be downward take the positive. Okay. So that means minus ky minus cy dot and plus f. So for this one we have is my double dot plus cy dot plus ky equal to f of t. So everything here y1. Sorry, y1. The y1 and f are the function of time. So that is the modeling and of the mechanical one single degree freedom mechanical systems. And this one, and in your vibration, you should be pay attention to how to do the modeling of many kinds of the combination of the spring and damper. Right? So that is your exercise. Hopefully you can exercise those things from vibration and take it to here for further things. So right now, if say if we have the formulation like this, for example, let me give any examples here. So say our system is say mass equal to 1, whatever the unit, and damper is say y1 dot, and so this is 2y1. Okay. So say the f of t say equal to 1, and to be assuming initial conditions equal to 0. So the question is how to solve for y1, right? So your homework 1, the exercise for your homework 1 can help you to answer this question. So that's the purpose we spent quite a bit, I think 2 lecture hours on this one. So again, to do this one, we can try is this. The plot transform of y double dot equal to s squared y of s and minus s y dot y0 minus y dot 0 plus y dot equal to s y of s and the plot transform y equal to y over s, right? So we take out this one. So therefore, after the Laplace transform, we have is y1 of s multiplied with s squared plus s plus 2 and equal to 1 over s. And here the plot transform of 1 equal to 1 over s. So simply we put into the Laplace transform of every single terms, and we come to here. So therefore, y1 of s will be equal to s squared plus 2 plus s plus 2, 1, right? How to do this one, then back to the this question here.
Well, you just gave us the answers.
I just give you an answer here. I tried to make out that example to match this one, save my time. Okay, so how to do that one back to our question 5 here. So this should be, I just erase it and yeah, so that is the answers to this one. Got it? Okay. So therefore, basically this one, using those numbers, the y1t should be equal to the output one and the question 5. Refer to that kind of one. So furthermore, and we like to do this, it's best to describe, and again, that is my personal experience. When you learn something dynamic, like vibrations, and just don't look at the calculation or the final result, the best way for you to grab any feelings about the system is to look at the curves. So for myself, my learning experience from the beginning is I always take my result and draw it into curve. I want to see how the system compared to other systems. Sometimes you can quickly get a feeling. So for example, say E minus T compared to E minus 25T, then you see how this is quick, this is slow. I mean, in terms of decay. You cannot get it until you see it. Okay, and the best way to see it is to draw the curve. And right now the tools is so popular than 30 years ago. That time we had to spend a bit rigorous to do this, but now you can quickly do it. Yeah, you kind of packed already. So why not today we stop and then we will continue on Monday.